Have you ever seen a single line of code bring down half a system? I have. Welcome to episode 62. Picture this: one tiny change to an API version and boom, chaos. It was a brutal lesson, but a clear one. In the world of software, compatibility isn't just a nice to have. It's a matter of life and death for your system. If you've ever felt the pain of a breaking change, or if you want to avoid it, you're in the right place. Today, we're diving deep into why compatibility is so critical. We'll explore key concepts like hooks, version management, and the idea of contract stability. By the end of this, you'll understand how to build systems that don't just work, but last. Let's start with a metaphor. Imagine a massive, bustling port. You've got ships, containers, and giant cranes moving everything around. In this port, the way a crane grabs a container is standardized. There's a specific type of hook on the crane and a corresponding attachment point on the container. This standard is our interface. It's the agreed-upon method for how two things interact. Every crane manufacturer and every container maker follows this standard. Things run smoothly. Now, what happens if a new, super efficient container is designed? The designers decide to change the attachment point to make it stronger. Let's call this version 2 of the container. This is a version upgrade. The problem is, all the old cranes in the port were built for version 1. Their hooks don't fit the new containers. Suddenly, these new, better containers arrive, but they can't be unloaded. The cranes try to grab them and fail. The entire port grinds to a halt. This is a breaking change. The new version broke the functionality of the existing system. The old cranes simply can't grab the new containers. Chaos ensues, shipments are delayed, and money is lost. In our software world, this is what happens when a service updates its API without considering the clients that depend on it. The system crashes. So how could this have been avoided? The solution is backward compatibility. Imagine if the designers of the new container were smarter. They add the new, stronger attachment point, but they also keep the old one. So the new containers have two types of attachment points. The brand new cranes can use the new, more efficient hook. But all the old cranes? They can still use the old hook that they're familiar with. The new containers work perfectly with the old cranes. This is backward compatibility. The new version of the component, our container, still works with the old systems, the cranes. The port continues to function without a hitch, and the upgrade can be rolled out gradually. New cranes can be introduced over time to take advantage of the new feature, but nothing breaks in the meantime. This brings us to our core insight. An interface is a contract. When you define an API, you are making a promise. You're publishing a contract that says, if you call me in this specific way, with these specific parameters, I will respond in this specific way, with this specific data structure. Other services or clients then build their logic based on this contract. They trust that you will uphold your end of the bargain. This creates a dependency. The client's code is implicitly dependent on your interface remaining stable. The danger comes from these implicit dependencies. You might not even know who is using your API or how they're using it. If you change that contract without warning, if you change the hook on the container, you're not just changing your own code. You're potentially breaking dozens or even hundreds of other components that rely on you. The destructive surface area of your change is amplified across the entire system. Every service that depends on your old contract is now at risk of failing. That's why compatibility is so important. Compatibility is the promise that the old contract remains valid. It is a commitment to not break the trust that other parts of the system have placed in you. You can add new features, new endpoints, new parameters like adding a new hook to the container, but you must ensure the old way of doing things still works. This principle is the foundation of robust, scalable, and resilient systems. When you treat your interfaces as unbreakable contracts, you create stability. Teams can work independently, trusting that the services they depend on won't suddenly pull the rug out from under them. Upgrades become smoother and less risky. You avoid the versioning catastrophe where a single change causes a domino effect of failures. It's about being a good citizen in your software ecosystem. You're not just writing code for yourself. You're building a component that others will rely on. Your responsibility extends beyond your own service. Now, let's think bigger. We've talked a lot about how changes to an interface can cause a system to crash. But what if the interface doesn't change at all? What if the contract remains exactly the same, but the system still falls over? Imagine our port again. The container hooks are standardized. Everything is backward compatible, and things are running smoothly. But one day, a massive supership arrives carrying 10 times the usual number of containers. All at once, a flood of containers hits the docks. The cranes, even though they can connect to the containers perfectly, are completely overwhelmed. There aren't enough cranes, there isn't enough space, and they can't work fast enough. The system gets congested, things start backing up, and eventually the entire port grinds to a halt. The interface was fine, but a massive spike in traffic, a sudden increase in load, crashed the system anyway. This is a different kind of problem, but it's just as deadly. In software, this is like your service suddenly getting 1,000,000 requests per second when it was designed for 1,000. Even if your API contract is stable, the sheer volume can overwhelm your resources, your CPU, your memory, your database connections. Your service slows down, starts timing out, and eventually crashes. And just like with a breaking API change, this can cause a cascade of failures throughout the system. So just ensuring contract stability isn't enough. We need another mechanism. We need a way to handle these unpredictable floods of traffic. In our port analogy, we'd need a way to queue the shipments. Maybe we need a holding area where containers can wait until a crane is free. This would smooth out the demand and prevent the cranes from being overwhelmed. What does this look like in the software world? How do we build systems that can gracefully handle unexpected spikes in load? That's exactly what we'll be exploring in our next episode. We'll dive into patterns like queues, load balancers, and circuit breakers that help you build resilient systems that can weather any storm. So today, we learned that an interface is a contract and that backward compatibility is the promise to honor old contracts. This prevents breaking changes that can bring down entire systems. We used the metaphor of a shipping port, where changing the container hook standard without thinking about the old cranes leads to disaster. But we also saw that even with perfect compatibility, a sudden traffic spike can be just as catastrophic. It's a reminder that building robust systems requires thinking about more than just the code itself. It's about anticipating how the system will behave under stress. Thanks for watching. If you found this helpful, be sure to like, subscribe, and hit that bell so you don't miss our next episode on handling traffic spikes. See you then.